Afternoon. My name is David Rolfe. I'm here from Volt. Before I start, could I have a show of hands here? How many people have actually heard of VoltDB? Okay, about a third. That's good to know. We won't fire marketing just yet. I'm going to talk for about half an hour to give you an architectural overview of what Volt is. It's intentionally somewhat conversational and goes more into the motivation behind it than into the deep low-level technical stuff. My experiences at conferences like this is when you start giving people very hairy technical presentations, you lose everybody within the first 15 minutes, except for the three guys who knew the whole thing off the top of their heads. So to start, why would you need to rewrite a completely new SQL database? What's the motivation? Why would you do that? And the answer is that a lot of the database technology we used was designed around 1985, which is when the traditional RDBMS kicked off. And at that point in time, a gigabyte of RAM was $7.5 million. It's now about $7.50. Now, the early traditional databases were designed on the assumption that RAM was spectacularly expensive, disk was just about affordable, and your job was to shuffle stuff in and out of RAM as efficiently as possible, and also to allow multiple people to do things at the same time while hiding it from each other. And that turned into a $35 billion industry, so let's not criticize it as an idea. But it's 2018, and continuing to try and progress based on an architecture which is based on completely different assumptions to the commercial reality is, I would argue, questionable. And we're also seeing that the RAM isn't the only architectural change we saw. We're seeing drastic increases in the number of cores, the expected cluster size. Virtualization was science fiction in the 1980s when this stuff started. So it's not surprising that the traditional RDBMS faced a lot of challenges over the last few years, initially from the NoSQL products and now from USQL products as well. So this brings us to what I would argue are the requirements this is what we at Volt find we hear from people. It needs to be support virtualization. Now, pretty much anything can be virtualized. It's just you won't enjoy the experience and it won't enjoy the experience. So what you actually need is a product which was built from the ground up on the assumption it runs in a virtualized environment, which means it has access to RAM, it has access to CPU, it may not have access to disk, to good disk, and it probably won't have access to good shared disk, which puts a lot of traditional databases into a difficult situation. ACID transactions, as far as we can tell, they're starting to make a comeback. It's very easy to do a nice demo showing that you don't need ACID and you can make your lovely application work. As you get into the enterprise and you have to glue 3 or 4 non-ACID compliant applications together, the number of possible ways it can go wrong is like one of those 1980s Japanese cameras with the 12 correct settings and the 731 wrong settings for every possible photograph. We're also seeing milliseconds are coming in. How many people here are connected with the phone industry in any way? Okay, 5G. The 5G phone standard says that you should be able to get a response in about a millisecond from your mobile phone application. A millisecond is 186 miles. That has massive implications for the database industry because it means you can no longer have one big centralized database in Omaha, Nebraska and having everybody communicating with it because the speed of light will kill you. It's like, it's I think 35 milliseconds between Europe and the US at the moment. So obviously, if you want low latency applications, you're going to have lots of swarms of databases pretty much in every neighborhood. The long tail. The classic thing is we can respond really quickly, but every now and then we might take a couple of minutes. A lot of any kind of IoT or machine-to-machine applications, which we do a lot of, if you're dealing with a computer program instead of a human, if it doesn't get a response, it'll probably ask you again. So you've got to be consistently very fast because otherwise it might start. You might find yourself being stampeded by a swarm of requests to ask the same thing twice. Complicated logic is something that Volt is very good at and something we're very keen on. The problem with the classic demo that's given for post-relational databases is it shows a really simple use case. Real-world applications, anybody who's ever looked at the code that was shown at a conference and the code that they ended up checking into GitHub with all the weird error checking stuff and making sure you haven't sent me complete garbage and that all the things that I'm passing you exist, all these things need to be done in real-world applications. And if you're dealing with a straightforward key value store, for example, you could get into a situation where you have to do multiple trips to the server to validate all your input data before you put it into the system. And especially if you're using some kind of schemaless architecture where you've got a big JSON object, life will get very interesting if the wrong stuff goes into the JSON object, because you no longer have a relational schema to say what the hell are you doing when you start putting in nonsense. So you can actually, instead of having bugs in the code, you can have bugs in the data. Scalability, the traditional database started off on one big node, and the big node kept getting bigger and bigger and bigger. And now with the world of virtualization, where everybody expects everything to run on clusters. But the interesting thing is that private clouds are a bit like business class in economy in airlines. The airlines advertise business class, and you see people in huge seats being handed cocktails. And when you actually board, you're down the back and squeezed in. So the average private cloud server we will be dealing with will be maybe 256 gigabytes of RAM and maybe 8 cores if you're good. So you now need quite large clusters, potentially. So having a product which scales to 2 and then crosses its fingers is not necessarily going to help you. High availability, I've been in the industry far too long. I probably need to find a different thing to do at this stage. When I started, high availability was pretty much rocket science, and now it's just supposed to sort of work. And that's a baseline requirement for anybody buying a database product now. Geo-replication, again, it's gone from being what I would call the Bond villain requirement, where I want to have 3 copies in 3 separate data centers in case 2 of them are destroyed by asteroids, so I can continue doing business even though all my customers are dead. I never understood that. I actually once involved in a disaster preparedness program for a major phone company where the assumption was that the data center would be completely destroyed, but the finance department would still have its checkbook. Never mind. And there's also this translytics HTAP thing. That's Gartner and Forrester, in the forest traditions of inventing buzzwords, have invented translytics and HTAP. And they both revolve around the idea of doing transactions and counting the data you're doing transactions on at the same time, which anybody can write 10 lines of code to do that, but you can't make it scale. So this is what we're seeing. And to go back, let's go on to the architectural bit. In college, we all did a college course on how the relational database worked, and it looks something like this. You've got CPU, you've got RAM, and you've got disk, and the RAM is precious and the disk is cheap. And your job is to how you've got multiple clients, the 2 guys there, both of which are doing this transaction. The transactions are running in parallel. And they're both doing things. And until client A finishes, client B can't see what he's done. And until client B finishes, client A can't see what he's done. So in addition to the cached data in RAM, RAM also contains explanations of who's allowed to see what. And this is a basic function of a relational database, and it's what made it successful. The problem is that over time, the hardware got more complicated. When you add a second CPU, you now no longer have to worry about what all the clients are doing, you have to worry about what the other CPU is doing. Because he could be about, or she, let's not be gender specific, she could be about to do something that you don't want done. And so you're now having, the level of complexity is going up geometrically. In fact, as I add lots more clients, and I add lots more physical servers, and I've now got 16 cores on each box, I've got 2 boxes, I've got 8,000 clients, it gets really complicated. Really complicated. And so you start to see traditional OLTP database applications start to plateau and become deeply problematic around 5,000 to 10,000 transactions per second. And that sounds like a lot until you enter the world of the IoT and until you enter the world of machine-to-machine transactions. So let's just visualize what this would be like if it were a supermarket. If we ran a supermarket the same way we ran a traditional database. I buy something, I go up to the checkout, I put it down. I then say, excuse me, and I go back off shopping. And the person at the checkout is looking at my stuff, and she's looking at the next person in the queue, pushes my stuff to the side, tries to process the next person's stuff. I come back, put another item down. Then another person starts doing this. It would be utter chaos. But this is how traditional databases worked, so no wonder they weren't scaling. So this problem attracted the attention of Michael Stonebraker, who, as pretty much everybody in this room would know, invents databases the same way most people file tax returns, pretty much one a year. And he looked at this and he found some really interesting things. What they did was they got an open source relational database, built an application, and then started disabling bits of it to find out where the slowness actually was. This is where I press the button on the remote, and I'm hoping I press the right button. Yes. What we found was that in a traditional database, keeping track of what's in RAM and getting it back onto disk is half of all the CPU time. Half of it. Latching and locking, which is the process of lying to all the other clients about what your client is doing and recursing that upwards, takes another 30%, which means that by the time you allow for index management, you're only actually doing about 12% useful work. And this is one of the reasons why NoSQL kicked off, because traditional databases were plateauing in performance. They couldn't handle beyond a certain scale. But the issue you face with NoSQL is you're giving up ACID, you're giving up a whole series of other things, you're giving up SQL, which turns out to be more useful than people realize. And so he wanted to say, well, why can't we build a relational database which runs really quickly and doesn't suffer from these problems? And he went all the way back to the graph I showed you at the start and said, hang on, RAM is cheap, it's getting cheaper. And if you look at most OLTP workloads, they can actually fit into RAM. Now, I spent about 25 years working with a very big relational database headquartered near here. And we were finding that for transaction processing applications, nothing ever made it to disk. It would go to the redo logs, but if we ever had to go to disk, we were dead. Everything we did had to be in RAM all the time, or we could never meet latency expectations. And so the only reason we had the SAN was in case we lost an instance, so the other instance could figure out what the dead instance was doing. That's the only reason it was there. And so there's a whole, so what he said was, okay, why don't we make this whole thing in RAM? That means that the task of logging and buffer management becomes a hell of a lot simpler. We snapshot it to disk at regular intervals, but we're not claiming to be transactional on that front. Instead, we'll use high availability to provide availability. And this is what we came up with. We partition the workload. We do a ring hash on your incoming transaction to figure out what kind of thing it is. And it goes into a queue. Now, inside each queue, all of the logic that you would have done as a client is encapsulated because we're using stored procedures. Now, before everybody runs out of the room screaming, bear with me. They're not as bad as you think. So these are requests to a stored procedure engine. And one of the rules is you can't have a request continue beyond a trip to the database. When I make a request, there's no such thing as committing afterwards. It either completes in its totality or it fails. Now, when the relational database first came out, the idea was I do insert, I think about it, I have a cup of coffee, I ask my boss, then I press commit, or then I do rollback. Nobody's done that since 1991. None of the applications we're dealing with now are with humans. It's all computers. They want answers. They're not in the business of going and getting coffee. They just want an answer immediately. And so we would argue, and we took the design decision that we do not allow transactions to outlast a trip to the database. So this means that these two transactions are completely isolated because all of the transactions for a particular subset of data are being handled by one CPU core only. There's a single thread running per core, which is taking a transaction, running it to completion, and throwing it back. Now, again, this is completely counterintuitive. Why would you do it that way? The answer is, if I've got 8 cores, and remember Tom Kite telling me this, we had 8,000 sessions and an 8-core box, and he said, well, why do you have 8,000 sessions? You can only do 8 things at once. He was right. If I've got 8 cores, I can only actually do 8 things at once. I can use all sorts of tricks in programming languages to pretend otherwise, but the reality is I can only do 8 things at once. So what we at Volt have done is accepted that reality and built the product around it. So we split up the workload by CPU cores, and not all of those cores have to be on the same box. They could be spread across a cluster. We take the line of requests we take the incoming requests, which are for named stored procedures, and we put them into a deterministic queue, a queue which is completely predictable. We do high availability by having 2 copies of the blue queue on 2 separate servers. So the client is actually sending requests to more than one place, getting both the results and doing an MD5 hash on them to make sure they are in fact the same, and returning it back to the user. What this means is in the event of an outage, the node goes down, the client sits there wondering what's going on, and it continues going with what it has. So when we have an outage, we have about a 1 to 3 second pause while we figure out whether the node is actually dead, and then we just keep processing. And so the worst case scenario is you may get a message back saying, I don't know whether this transaction finished or not. That's about 1% of everything which was in flight at that point in time. So to come back to it, we split up the workload by core. We have a deterministic queue which can be replicated to multiple places. Within RAM, I only ever have to worry about one transaction at once. I'm not in the business of keeping 500 transactions going. And I can flush it to a local file system because I've partitioned everything. I don't need a SAN. We found that this is about 12 times faster than a traditional relational database. So it's ACID, it's really fast, it's very asynchronous, high availability comes built out of the box. And if you actually think about it, this is how supermarkets work. You join a queue, you work your way to the front of the queue, you're not allowed to change your place in the queue, you're not supposed to go putting stuff into your trolley once you get to the front of the queue. And so as a result, we found we have a SQL ACID compliant database which is doing around 7,000 to 9,000 transactions per core per second. So what does this give us? Our goal is to be in the center. Traditionally, if you wanted ACID transactions and you wanted to do it in milliseconds, you would you'd do a legacy OLTP system. That's what they were for. But they didn't really scale. If you wanted to do lots of stuff, like in the billions of records a day, you could do a batch processing approach or Hadoop approach, but that would definitely not get it in milliseconds, more like half an hour. And if you want answers but not necessarily 100% correct, which is for a lot of applications is fine, but for certain things it isn't, you could do your traditional NoSQL key value store. You get answers very quickly. But if you're in the business of allocating finite resources, accounting things, it might be a bit scary sometimes. Vault tries to get into the middle. Hang on, wrong damn button. Vault tries to get into the middle, and it tries to offer you milliseconds, transactions, and scale. Obviously, there's design compromises. The compromise we make is that we partition the workload, and that everything must fit into RAM. And you end up having to use the store procedures. Our store procedures are written in Java, with callouts to an underlying C++ engine. So the core of the product is C++, which means we don't have memory management issues, we don't have garbage collection issues. The actual store procedure language is basically implementing a Java interface, extending a Java interface. And to come back to this, before everybody, in a vain attempt to persuade people that store procedures aren't totally insane, traditionally, we did many SQL statements, and we started a session. And that created the problem I described earlier, that it got really, really hard for the database to keep track of what everybody's stuff is looking like, because there's 1,000 people changing things at once. Conceptually, it's really simple. In the client-server era, it made a huge amount of sense, because things were moving quite slowly. People could do the programming logic on the client side. But we know it doesn't handle scaling OLTP loads. And we know there's locking issues as well, and transactional issues. Also, if you have a failure of a node, you end up with locked records somewhere. You end up with records where it takes a while for the database to figure out that the client isn't coming back. So when we had 100 PC desktops speaking to a single node server, this wasn't so bad. But if you've now got 1 million web clients speaking to 2 application servers and one of them goes down, half of all the connections are now dead. Everything that was locked by those half of all the connections is still locked, and all those sessions are going to come back about 2 seconds from now and try and lock the record. So that's why we felt it wasn't going to work. The traditional NoSQL key value store is to move all the data back and forth again. It works for a lot of applications, but in anything where you're competing over resources, you're allocating finite stuff, you're counting, you run the risk that 2 people will start trying to do the same thing at the same time, and you'll start clobbering each other. Now you can tell fairly easily if you've been clobbered and somebody's gone and changed it before you, but then you have to retry, and that will lead to a long tail, which is what people don't want. If you've got a very complicated application where you have to make 3 or 4 changes at once, you could then have this really weird, complicated daisy chain of things that you have to update in sequence, and the consequences of not being able to up to the middle one get really complicated. Which is why we ended up with stored procedures, which are not something you get books at Christmas about. At least I don't anymore, thank God. But they are predictable, and by moving the logic to the server, you get it really close to the data. And when people do that with Hadoop, everybody thinks that's great. So, the last thing I'd say is we've been around a while now. We're not huge, but we have a really interesting list of customers. Our early adopters were the phone industry, because the phone industry has been ahead of everybody else in the virtualization curve for some time. The phone industry has been dealing with ridiculous volumes and with everything going over the top. And the reason they went for virtualization, the reason they were pushing it wasn't because they liked the technology, it was because traditionally nobody could actually size systems properly. So what would happen is they go to the developers and they say, well, what do you think it will need? And he'd go, I don't know, make a guess. His boss would add a little bit of padding to be sure. Their boss would add a little bit of padding to be sure. And by the time it was deployed, it showed up in a truck. And so I was once sent to measure the performance of an OLTP system in Atlanta for a well-known phone company. And at busy hour, it was running at 2%. And that was because by the time all the layers of middle management had added their padding to the estimates, it was huge. And that's a fixed cost. That hardware's being built, it's being paid for. So the reason they went for virtualization was so that they could build it, they could deploy something small and then grow it. And they'd rather grow it over the time and pay more money over time than make a massive capital investment up something where they can't predict the demand. So yeah, we started out in finance, in telcos. We are seeing the classic Vault use case. I'll give you really one interesting example will be the Financial Times, where they're using it for managing your journey through the website. If you're a subscriber, every time they have all this data, this machine learning and this modeling going on, and they figure out what kind of customer you are and what kind of stories you might be interested in. Chinese equities, say, great. So you log in and they show you a thing on Chinese equities. The moment you've read one story, your position has changed slightly. And so the act of advising people about something is actually a transaction. If you think about it, it needs to happen only once. If for example, another classic use case would be in online gaming. That would be, did they actually they didn't put it on the slide, they're out of space. Okay, well, for online gaming, people use it for instrumenting the games. So you can figure out if you're fighting the dragon and you're about to die, it becomes a remarkably opportune time to sell you a dragon shield. But that involves knowing exactly who you are, knowing all the demographics, and making sure you only make the offer once. Because otherwise you'll look like a fool and they won't be able to play the game because there'll be 1,000 modal windows coming up offering them the dragon shields. It's a transaction, guys. It just is. With that, I've got a couple more slides. The thing which is really popular at the moment is machine learning. You know, if you're not machine learning, you're nobody. And because of our ability to put logic into the server and to maintain very fast speeds, because in practice, when we do, say, 7,000 transactions per second, that's effectively the cost of going to the server and back again. Doing additional SQL statements once you're there is very cheap indeed. So this is a really interesting use case. Huawei are using this in China for credit card fraud prevention. So they've got the obligatory data lake, they've got the obligatory machine learning going on, and they generate rules which are expressed as Java classes, very big Java classes. There's about 1,500 rules that get run every time you show up and try to buy something. And all of this logic is expressed in Java, and it gets loaded into Vault. And so what happens is you show up, you try to swipe your card, it knows who you are, it knows what kind of person you are, what your buying history is, exactly which store you're in, the kind of things which have been known to go on in that store, and it comes up with a score saying whether they should approve the transaction or not. So traditional credit card fraud prevention is half an hour afterwards, they say, hang on, you did what? Right now in China, they're saying they're not going to do it. They just decline the transaction on the spot. And it's another example of this being transactional, because the moment I've been declined once, that ought to have a pretty important bearing the next time the model is run for the same user. If you're getting if you've had 3 transactions declined the last half hour for different reasons, that's starting to get very suspicious. So, if anybody is interested, the core of the product is C++, but we have Java on top, so pretty much anything which runs in a Java virtual machine can be expressed as logic in Volt, provided it doesn't speak to a third party outside the database, because we could be running more than one copy at once for high availability purposes, and if I go speaking to another website, 1, you're going to be speaking to it twice, and 2, one of the messages might get back, and then all of a sudden, a bit different, you've got a form of split brain going on. So you can't speak to the outside world, but you can do pretty much anything else. So the key thing for us is, hang on, it has to be deterministic. Everything about Volt is very, very dull and predictable. So for example, when you put in a transaction, it goes into a deterministic queue where everything gets executed in the same order all at the same time. Our requirements for stored procedures is that they're deterministic. We don't do random orders. And our requirements for this kind of logic. So we know that we've done this in H2O and JPMML. And if anybody wants to see examples, I can give them to you, but it's not suitable material for a conference because nobody, unless you're about 12, you won't be able to read the slides. And so we've done it in H2O where you basically take the POJO and you bring it in and you use it. And we've also done it in JPMML or PMML, which is the other thing that seems to be popular. So with that, I shall stop rabbiting on and pause for questions. Yeah. Yeah.
It's almost like you're basically doing the old punch cards into the tray, and you're using one resource sequentially very fast.
Yes.
What happens when there are actually conflicts between different jobs for the same resource? That's one question. And what happens when you have really long-running jobs that are doing inserts? And finally, you say you're using Java to see. Are you using J and I, or what are you thinking?
We use what's the mechanism for getting from Java to C? There's a mechanism for getting from Java to C++ we use to get down into the C++ layer.
Yeah.
My experience
with J and I was it was very cumbersome to marshal all of the attributes into the.
I've got some smart co-workers, what can I tell you?
No, I mean,
Okay, so, yeah.
I mean, I'm a C guy.
Yeah.
So that's okay. But I'm curious as to how you actually take advantage of your self-contained job when in fact there are inter-job.
Okay, so there's basically a couple of questions, and if I forget one, prompt me because I left Dublin yesterday and I left Boston at 6 a.m. this morning, so at this stage I don't even know which way is up. Never mind, in a position to answer questions. The first thing is that we take partitioning deadly seriously. We partition the workload. So if you are going orthogonal to the partition key, you kind of have to get all the partitions to cooperate, which is obviously much slower. So the ideal Volt workload is inherently naturally partitioned. Things like user sessions is fine. If you get into the business where I have to lock multiple resources which can't share the same partitioning key or have to work with them, we support it, but it's inherently much slower. I don't know of any product in the world that doesn't struggle in that situation. The second point you raised was what happens about long-running jobs. That's an excellent question. We don't like long-running jobs. It's another architectural constraint, and congratulations to you for spotting it. We live in a world where we expect our workload to be OLTP. We expect millions of transactions to show up. We expect lots of people want really rapid answers. If you start using Volt to answer questions like who lives in the red house and owns a kangaroo and is less than 3 miles from a subway station, we're not an ad hoc product. And again, it goes with the whole being deterministic. Anybody who has worked in the high-performance OLTP space would know that the reality is you can't share hardware with ad hoc people when you're trying to run an OLTP system. You'll have a resource issue at some point. So it is an issue, but it's not necessarily one that affects us that badly.
What about a bulk loader, which you've got like thousands of records that you want to, that's one job.
We have a bulk loader, it doesn't get in the way. We have a bulk loading API. It basically batches them into micro batches. So we don't, if I want to load 1 million records, I can't do that as a transaction. I can load it very quickly and it will tell me if it didn't work. But the bulk loader's performance is surreal. It's really vast. Yeah. And what was your last question?
Well, it was about the J&I, C++, the Java interface to C++.
You don't see that as a developer. As you're writing for Vault, you work in Java. You don't have, yeah.
My question was really a performance issue.
If
I was wondering how many times, is that like compile once many times? Do you have a pre-compiler that will set the hooks into that, or do you have to process it every time you see that?
I would love to tell you I knew the answer to that question. If you give me my details, I'll actually speak to our engineers and find out, because I don't like not knowing the answer. Next.
So how well it is suited for number crunching applications? So which is sometimes batch in nature, long running.
Counting. Now define counting. So for example, we have this.
Joins, aggregates, and then counting.
Okay. We have this concept of, see, the problem you're saying is, okay, great, we love lots of small transactions. You've just presented me with one which is inherently a big transaction. We have this thing called a materialized view. Now, traditionally, a view is a SQL statement disguised as a table. When you reference the table, it fires the SQL statement and then the fireworks kick off. Our views work completely differently. When you create a view for Vault, it's effectively saying, every time I update the parent table, it updates the view. Now, there's one copy of the view for each partition you have. And when you query the view, we just join the 8 rows from the 8 partitions. So adding a view in Vault has about a 1 to 2% performance penalty per table. I don't know how they did it. It's surreal. I actually got examples I can show you right now if you want. So we are being used for MiFID II compliance in the City of London, which is this finance thing where all these guys have these mutual funds, and the mutual funds own other mutual funds, and they have rules about who can do what. So you might be told you can only spend so much of the pension on Venezuelan Bolivar futures. And it used to be you had to check that once a day in the middle of the night. Now it has to be done 4 times a day. And the industry has a horrible feeling it's going to be real time quite soon. And so Vault's materialized view stuff is really good for that. And it almost came out as a side effect of the problem we were facing with people like you were asking the question, well, how do I count things? So we invented something which makes it really good. So we also have, so I think that's that question answered. Yeah. Next.
I have a follow-up.
Yeah. Sorry.
We're great for transaction processing. Now we want to get to something where I want to sort and order the database across partitions. How do you handle that?
That comes back to the multi-partition transaction. And so we slow down. Multi-partition reads are slower. They have to be because there's more coordination going on. Multi-partition writes are slower still. But in practice, the vast majority of the workloads we would see, now this could be survivor bias, some people that end up using Vault, are ones where you have very naturally partitioned workloads. Yeah.
I don't know a lot about the product itself.
Yeah.
This is the first time I'm looking at it. We're users of Ignite.
Yes.
And our primary reason is we want fast data.
Yeah.
We do reporting. Ignite has Ignite SQL, which kind of makes it easy for
Yeah.
us because most developers can write SQL.
Yeah.
And that's why we use it. So why would I want to use this over Ignite?
I'm not going to I don't know enough about your situation to prescribe anything. I think one of the really interesting things where we are now is when I entered the business around 1992, that shows how old I am, and there were only 4 databases, and which database you used was like a religion, being born into a religion. You were a Solaris shop, a DB2 shop, or a SQL Server shop. That was about it. And around the 2005, when NoSQL kicked off, that all got thrown out the window. And the really interesting challenge you guys now face is developers and the development community now has to pick databases. And that's not something we went to college. That's not something we got a lot of experience in. It's like changing religion. You tend to define what you want in terms of what the last one isn't. And so I don't know enough about your use case to say whether you should be using Ignite or anything else. And I'm not going to stand in an in-memory conference and diss other products. I will say that all of the in-memory products tend to be very different. And what's really interesting is we generally don't see ourselves competing with Ignite. They don't seem to be competing with us. It's such a small and diverse industry right now that we don't seem to have that many conflicts. I'm happy to go into detail later if you want.
So our use case is simple. We have lots of data.
Yeah.
But we only really want to report on certain parts of data.
Yeah.
So
Yeah,
fast
yeah.
to query. We don't really want to transform the data or anything.
Yeah.
We just really want to pull that, put it in memory, make it really fast.
We have people like the phone industry uses us for caching session. We use it as a cache, and it's really infuriating. We've all these wonderful SQL features, and what a very well-known phone company with its headquarters outside Helsinki, with previous investments in forestry and tires, uses us, and they're actually using us as a cache. I don't know why, but so I don't have enough information about your use. I'm happy to talk, but I'm not in the business of standing up here and claiming that our product is the wonderful solution to everything and it will cure cancer, because we're all too old to listen to that pitch at this stage.
So if I take this back, what would I say? VoltDB is what?
It's a really fast transactional database that gives you ACID, speed, and scale. In fact, hang on. It's that. We try now. Let's be honest. We're all grown-ups here. We've all been in the industry a while. We all know that there's no such thing as a free lunch. There are always compromises made. We made our compromises. We said that we're expecting a partitioned workload. We don't like long-running transactions. And we can get you into this sweet spot, but there's compromises made. And it's like designing a race car. If I want a car which goes around a racetrack really quickly, I end up, with an Ariel Atom or a McLaren. That car is excellent at that job, but useless for school runs. Traditionally, databases were like minivans or large pickup trucks, extended cab pickup trucks, and there was one car for everything. Now, everybody's making different vehicles. I think it's great, but you do need to be careful deciding which vehicle you want. And I would say that as a prospective consumer, do your research, download it, play with it. Don't believe the vendors, don't believe me. Try it in your universe and see what works for you. Because what works for us and our existing customers might not work for you, because there may be they may hit technical issues about how they need to do things. They may even be cultural issues, because a lot of it, we tend to ignore the cultural aspects of a product. Certain products make assumptions which are actually quite deep. So for example, I was recently working with Akka, which is not a database, but it's a sort of transaction processing engine which makes a virtue of being unreliable but extremely fast. It's sort of like UDP for messaging. Now, that's great. If you like that, that's great. But I can see a lot of people going, oh my God. Next question.
So I want to understand a little bit more about your partition flexibility.
Yeah.
So in terms of scaling up and down.
Yeah.
And also partition strategies and changing of partition keys.
Yep. Elastic scaling up is done. We use a 64K ring hash to partition the data, and then blocks are handed out to each protocol. So scaling up is a case of reallocating the records. Scaling down is obviously much harder for anybody who's actually tried it. What we generally see is that it's the kind of feature people always talk about, but may not use that much in practice. Because the economics of it, the fantasy solution where I'm going up, shrinking and expanding my cluster as the day goes on, it makes all sorts of weird assumptions about the fact there's something to expand to. Because a lot of virtualization is a bit like running a dodgy bank, in that you're hoping nobody ever wants all the resources at once. Next question. I think I'm running out of time here. The man at the back is giving me 5 minutes. Either that way he's giving me a high five. Oh, he's giving. If you change the partition key, you can, but that's an expensive multi-partition transaction. I'll be honest. We made compromises.
Just one question on determinism. How do you validate that, or is that up to developers? You damn well better use an order by in your queries. And if we can figure out when it's not deterministic, and we will complain. And if it starts with everybody says, well, why would it ever do that? And the answer is, if a node goes down, and when a node goes down, when it comes back up, it doesn't get anything off disk. It asks another node for the data. So you could, in theory, get stuff in RAM in a different order at that point. And so with most distributed databases, all these modern data, it works fine when it's working. The failover is now not the problem. It's the rejoin that kills you. Any more? How do you handle referential integrity constraints? Because you can expect the parent key and the child key to be in different partitions.
That we do not enforce referential integrity constraints. You'd have to do it at the application level. Now, there are performance reasons for doing that. When between Oracle 6 and Oracle 7, they started enforcing referential integrity constraints, and applications slowed down, in my personal experience, by about a third, simply because of the extra work that was being done. But that's an issue. But on the other hand, we're now talking about referential integrity constraints, which means we're firmly in the SQL universe. Have I exhausted people?
So a small question regarding the diagram that you showed for your review with Java procedure.
Yeah.
Going before one. So you have queues for every code.
Yeah.
If I have a procedure that's going to work on row 1, it goes to core 1.
Yeah.
Another procedure who also wants to work on row 1.
It queues up behind the first one.
So it locks up.
Well, no, it's not locking up. The first one is working. Nothing ever gets to wait for anything. You're not allowed to wait. You're at the front of the queue in the checkout. You don't get to go off and do anything else.
But there are two different cores, right? So
Oh, if they need the same resources, then you have to do a multi-partition transaction, which is which is obviously slower. And again, this is the compromise we make. We're betting that the vast majority of the workloads are partitioned.
are you losing consistency then? Like you may be changing it, but I'm getting it a different.
No, that we have the best consistency in the industry. We've got the Jepsen test to prove it. Have I finally exhausted people?
Do you support more than 2 copies of the data?
Yes. How many do you want?
You said you have 2 jobs. So
Yeah. I use that for explanation. Financial services generally go for 3.
What happens to latency then?
You get a latency drop-off when you go from 1 copy to more than 1, and then it's pretty much the same. Because going from 1 to more than 1, your life has got more complicated. You now have to tell more than 1 person. Generally, we probably, I mean, in terms of latency, you're talking, the average Vault transaction is under a millisecond on a LAN. Are we done? I'm out of time. The man's going to get very cross with me soon. Yeah. He just gave me 1 finger, so I'm assuming that means I've got 1 minute left.